Zoom recording. So today we're going to do redox, so the beginning of the redox conversation, and we're going to keep doing it on Monday. So do any of you talk to the first section? Do anybody of you know the first section people? Do you regularly talk? Did you hear like how it went today?
Yeah, somebody told me it was hard.
Okay, so they're pretty, when we left, I can feel the tension in the class. So it's not hard, but I always say that, right? But it is not hard. It's just you have to practice. Just like when I said about the nomenclature, you got to practice. If you practice, and you have a whole week, right? So you got to start now. But the process, I think what they think is hard is that last part that we're going to do. Okay, but so let's get started. First of all, we're starting the conversation of redox reaction. Redox means reduction and oxidation. They just put it as an acronym, redox reaction. So for us to do redox reactions, we have to learn oxidation states. Okay, so a reduction oxidation reaction is basically, actually, does anybody know? Can anybody tell me how do you know something is a redox? Does anybody know that?
You gain and lose electrons.
That's it. That's exactly right. So it's as simple as that. If you gain or lose, if you transfer electrons, if electrons are transferred in a reaction, then that is considered a redox reaction. So for us to know, okay, so you're probably like saying, okay, so then how do I know if something transfers electrons? That is what oxidation state does. So first, we have to learn how to tell the oxidation states of every single element in a reaction. And then we say, oh, okay, this gets reduced, this gets oxidized, so therefore, there's a transfer of electrons, so therefore, this is a redox, okay? The easy part, I mean, I think for me, the easy part is getting these rules down, because these rules, you see there's 7 of them, and it seems like a lot, but it's really not, because most of the rules are similar to what we've learned about charges. Okay, so you're going to see a lot of things that when we go through these rules, you're going to be like, oh, that's just like the charge of this. Oh, that's just the charge if I look at the periodic table. So it's not a lot of new stuff. It's just you're applying it to a different thing, which is called this oxidation state. Okay, does anybody know, besides what's written there on the screen, but can anybody, well, let me not even ask. Let me just go ahead. If you guys have a question, you got to interrupt me, okay? Because there was a lot of questions in the first section. So the first thing I want to say about oxidation state before we start talking about the rules is it's not a charge, okay? Let me say that again. Oxidation state is not a charge. So remember how when we talk about ions and I say, okay, so what's the charge of oxygen? And oxygen is always -2. Why? Because oxygen is in the 6th column and it wants 2 electrons to get to 8. So that's a charge, right? Oxidation state is not a charge. It may seem like it's the same, we're talking about the same thing, but it's not the same thing. It's hypothetical. Look, it's right there in the first bullet. It's hypothetical. So it's this hypothetical state if all of the elements in a compound would be 100% ionic, or in other words, would lose all of their electrons. And why it's hypothetical is because this oxidation state thing is applied to covalent compounds, right? So ionic compounds have charges because they lose or gain electrons. But you have oxidation states being applied to both an ionic compound and a molecular compound. And molecular compounds don't have ions, right? Water doesn't have an ion, right? I don't know, methanol, if you remember, or methane, CH4, that doesn't have an ion, right? But you can talk about the oxidation states of methane, of carbon, and you can talk about the oxidation state of hydrogen in a methane molecule. So it's not a charge. Another way that you can kind of prove it to yourself is oxidation states can be a fraction. And I'll show you. We'll do the first thing there, the second bullet, iron Fe3O4. You'll see that when we calculate the oxidation state of iron, is going to be a fraction. So that tells you right there, it can't be real. It's hypothetical because there's no charges that is a fraction. You either lose or gain 1, 2, 3, 4, or whatever number of electrons. You don't gain a fraction of an electron. So does that make sense so far?
Yes.
Okay. So, let me just reiterate one more time. It's not a charge, so do not call it a charge. You have to call it an oxidation state. It's hypothetical. It does not really exist. It is basically saying if this atom, if this compound, right, these elements connected together would be 100% ionic, or in other words, would lose 100% of their electrons, this is the state that they would incur, the average state that they would incur. Okay, so it's a theoretical thing. Okay. I know we do not know the rules yet because we haven't gone over them, but just pretend we do. And when you see a typical problem might be, oh, can you give me the oxidation states of every element in this compound? This particular compound that I'm going to do is Fe3O4. Okay. So one of the rules is for oxygen. We haven't seen it yet, but if you look, it's where's oxygen? Yeah, for number 3, right? So number 3 talks about oxygen, but the rule for oxygen is the oxidation state of oxygen is usually -2. So what you would do to find the oxidation state of iron is first of all, wait, let me back up. You are always going to know the oxidation states of everybody except one, right? So, and it's usually that's usually how it works, because that way you can solve for the one that you don't know. These numbers that you're looking for, you can solve for one of the oxidation states. So oxygen is a really common one. Oxygen is usually -2. So I would put a -2 right on top of the oxygen. And then to find the oxidation state of iron, I have to kind of turn it into an equation, like a math equation. I would equal this equation to whatever the charge of the molecule is. Does this remind you of something that we've done before?
Yes, it's on the
What?
tip of my tongue, but I can't remember.
So when we first started talking about ionic compounds, right? Like if I wanted to figure out what the charge, right? Not the oxidation state, the charge of something would be, I would equal it to 0 if they had a 0 charge, or I would equal it to, yeah, it would be to 0 because ionic compounds will always end up being neutral. You remember? So it's the same thing. It's sort of the same thing, but it's not a charge. It's now you're doing it for this thing called oxidation state. So anyway, I would equal this equation to 0 because Fe3O4 is an ionic compound, and therefore there's no charge of the molecule. Okay, so I have 4 oxygens, and each oxygen, because remember I'm solving for iron, so I have 4 oxygens. Each oxygen is a -2. So what is the total oxidation number of oxygen? Can anybody guess?
-8.
Right. So it's just exactly the same as we used to do before with the charge, right? So 4 times -2, because each oxygen has a -2. So that would be -8. And then I would add it to whatever else is in the compound. I only have to do one more, which is iron. Since there's 3 irons, I would put 3x, and then I would solve for x. So if I solve for x, look what I get. I get 8/3. So what does that even mean, right? That's why these things are hypothetical. It's not a charge because you have a fraction. The oxidation state of iron in Fe3O4 is 8/3. Okay, so do you understand at least the process and the difference? And you have to make sure you understand that it's not a charge. And what's the word I'm looking for? I have convinced you that it is not a charge, and you're okay with that.
Yes.
Okay.
Yes.
Okay. So then the last bullet I do want to talk about is important because considering that we just talked about reactions and multiple ratios and all this, and all this stuff, coefficients have come into play sometimes when we do all those kinds of problems. So it's important that we know how to answer this particular question for oxidation states. So the question is, do we include coefficients when finding oxidation numbers? So for example, if I had 2 Fe3O4s, right, 2 of those compounds, would the oxidation states of those atoms be different or the same?
Different? The same?
I love it. It's two different answers. So the answer is it would be the same. It would be the same. It wouldn't be different because all the coefficient is telling you is how many of the compound you have, right? It's not changing anything about the compound. It's just telling you you have that many. So regardless if you have 100 Fe3O4s, all of the ions in an Fe3O4 compound is going to have the oxidation state of 8/3. Does that make sense? Are you okay with that?
Yes.
Okay. So any questions before we actually move into the actual rules? Any questions, general questions? Okay. So by the way, that's called iron magnetite. Believe it or not, this guy, the common name for it is iron magnetite. Weird. But anyway, okay. So rule number one. Rule number one says free elements and uncombined states have an oxidation number of 0. So for example, in a reaction, maybe you have something like this, magnesium, and it's by itself and it's a solid, right? So if you see this in a reaction and they're asking you to put oxidation states, you would put a 0. So you put a little 0 on top of the magnesium, because anytime you see something by itself and in its most natural state, then you would assign it a number 0. Are we cool with that?
Yes.
Yes.
Okay. So it's important that you understand the second part of that, right? So I said anything that's by itself, free element by itself, or if it's in its most natural state. So for example, if I was to look for oxygen out in the world, how would I find it? Would I find just one oxygen? Would I find when I analyze it, is it just one oxygen?
It would be 2.
It would be 2, right? And there's a couple of elements that do that, right? The Broncliffe or whatever, the bromine, iodine, nitrogen, oxygen. So all those people, those 7 diatomics, those naturally come as diatomics. If I was to search for them, they would be in a pair. They wouldn't be by themselves. So if I saw this, which we see this a lot, right? We talk about oxygen gas or O2 or N2. We do that. We've talked about it a lot. So if we see one of those things in a reaction, then I would have to put an oxidation number of 0, because that's how you naturally find it. Even though it's not quote unquote by itself, it's not connected to anybody else. It's just, it lives with another of itself to be stable. Okay. So you got to know both parts of that number 1 rule. Are you guys cool with that?
Yes.
Okay. Okay. So number 2 is really easy. Number 2 says in monoatomic ions, the oxidation number of the monoatomic ion is the charge. Somebody give me an example of a monoatomic ion.
Sodium.
Sodium
plus.
Right, so sodium plus 1, right? So let's say we had this in some reaction, right? That's a little aqueous. If that's part of a reaction, then the charge, or the oxidation state of sodium, because it's a monoatomic ion, would be +1. So I would put a 1 on the or whatever, +1 on top of that. Okay, so that's what that means. Simple. Yes, I can move on.
Yes.
Okay. So the oxidation number of oxygen is usually -2. Well, that's freaking awesome, because that's usually that's what the charge is of oxygen too, as well. So you're not learning anything new. So whenever you see an oxygen, like we did up here with the iron magnetite, you would assign it a -2. There is an exception, and it's when peroxides, that's hydrogen peroxide right there, this H2O2, it would have an oxidation state of -1. But guess what? I am never going to give you peroxides. So you don't have to worry about it. I'm so awesome. So really, you don't have to learn anything new. When you see an oxygen, put a -2 on there, and that's it. Everybody cool with that?
Yes.
Yes.
Okay. Hydrogen, really easy. Because look what it says, hydrogen is usually +1. Well, great, because usually hydrogen is 1 anyways. It's a proton. So the charge that hydrogen would take would be +1, and also the oxidation state that it would take would be +1. Except, and this is a big exception, this you do have to know, except when it is bonded to a metal in a binary compound. So for example, look at this right here, LiH. LiH is called lithium hydride. In this case, the metal, see, I've said this a couple times, right? Metals cannot be negative. They cannot be negative. They're much stronger at reducing than any other stuff, right? Then especially a non-metal like hydrogen. So when hydrogen is bonded to a metal in a binary compound, then the lithium, the metal, will take the positive, and the hydrogen will take a negative one, which that also should be like, oh, that's why that's not a charge, because hydrogen does not take a -1. Hydrogen does not do that, right? So this would be a -1, and this would take the +1. Are we okay with that? This one you got to remember.
Yes.
Okay. I hear the same 4 people saying okay, so I hope everybody else is okay as well. So anyway, 5, super easy. We're not learning anything new. Look what it says. Group 1A, metals. So that's the people in the first column. What's the charge of people in the first column always?
+1.
Exactly. So the oxidation state, exactly the same. So you don't have to work, you don't have to learn anything new. So everybody in the first column always has an oxidation state of +1. Everybody in the second column always has an oxidation state of +2. Great. And then one other thing that never changes is fluorine. Fluorine is always -1, always. And that's great, because usually when you do something, when you ask for the charge of fluorine, it's -1 because it's in the 7th column. Okay. The last one, because actually you don't even have to know number 7, because I'm never going to give you a superoxide ion, right? So the last one that you have to know is really easy, because we just did it up here with the iron magnetite. So can you guys still hear me?
Yes.
Yeah,
Yes.
okay, because they're vacuuming upstairs, so just let me know if you can't hear me. Okay, so number 6 says the sum of the oxidation numbers of all of the atoms in a molecule or an ion is equal to the charge of the molecule or ion. So for example, remember up here how we equaled it to 0? Why did we equal it to 0?
Because it's not a charge.
Because there's not a charge on the entire thing, right? So that's what that means. The sum of the oxidation numbers of everybody involved is going to equal whatever the charge of the molecule is. The sum of everybody in Fe3O4 is going to equal to 0 because there's no charge on the molecule. So if I had nitrate, right, and I wanted to find the oxidation state of nitrogen or whatever, but whatever, regardless, I wanted to find the oxidation state of everybody, who would I equal it to?
-1.
Right, because the nitrate has a -1. This is exactly the same what we've talked about with charges. So is everybody cool with these rules? Because you need these rules to be able to do a redox reaction.
Yes.
Yes. Yes.
Okay, cool. So this is the chart in your book. And I want to take a look at it for a sec. Oh, okay. I want to take a look at it for a second so you guys can kind of see, first of all, that they're not charges, because look at like nitrogen, for example. Nitrogen, when I say, oh, what's the charge of nitrogen? You guys go -3. Why? Because it's in the 5th column. It wants 3 electrons, yada, yada, yada. But look at all of those different oxidation states that it's possible to acquire. And why are there so many different oxidation states? Because it depends on who it's being connected to. It depends on if it's an oxygen, it depends if it's connected to aluminum, it just depends. So whoever it's connected to determines what the oxidation state of that element will be. So look at chlorine. And the reason I point these out is because remember I told you when you find the oxidation states of everybody in a compound, there's always going to be one that you don't know. So you have to solve for that one. So my point is, you do not want to ever mistake nitrogen or chlorine. Like that's the one that you never know. So don't think, oh, chlorine, it's -1 because it's in the 7th column. It's not a charge. So you always have to solve for chlorine. You always have to solve for nitrogen. The ones that have a ton, right? A ton of oxidation states, you've got to solve for. But then look at the ones that are always the same, right? So the first 2 columns, always the same. Fluorine, like it said in the rules, always the same. Boron, everybody here mostly is always the same. So just it's cool to know the trends, right? The ones that you always can count on and the ones that you always have to solve for. Do you guys understand?
Yes.
Yes.
Okay, so let's actually do some problems then. So the first one is super simple, right? Because actually the first one, what is it called? First of all, what is Li2O called?
Lithium monoxide.
Lithium monoxide, correct. Well, nope, that's wrong. I was gonna say you were right, but that's wrong. What type of compound is it?
Oh, is it lithium oxide?
Right, it's lithium oxide. So you should know the oxidation states of both of these without having to make a little math equation. What's the oxidation state of oxygen?
-2.
-2. -2. What is the oxidation state of lithium?
+1,
Why +1?
because it's in the 1A column on the periodic
Right,
table.
exactly, because it's in the first column, and those are always +1. So that's it. I mean, that's literally what we're doing, is we're assigning little numbers to everybody, okay? So for the next, whatever, compound, what is that called? Does anybody know? And I would put this to make it easier for you, AQ.
Hydrogen nitrate.
Nitric acid.
No.
It's not hydrogen nitrate. Nope. It's an acid.
Nitric acid.
Nitric acid. Good job. Okay, so which is the element here that we should solve for?
Nitrate.
The nitrate?
Would it be the hydrogen?
Why are we solving for someone? Because we don't know it, right? It's going to be the X. So you have to remember the rules, because the ones that are always the same, well, that's the ones that you don't solve for, right? So hydrogen is usually what?
+1.
+1. Exactly. So you wouldn't solve for hydrogen unless it's, it's always +1 unless it's with a binary compound in a metal, right? But it's always +1 other than that. Oxygen is always what?
-2.
Right. So the answer to my original question was you would solve for nitrogen. Because if you, again, look at nitrogen, look how many different oxidation states nitrogen has. You can't tell me that nitrogen, you don't know what nitrogen is, because it depends on what it's connected to. Okay, so that's the answer to that question. So we got to solve for a nitrogen. So how do we set up the math problem?
Let's see.
Would it be 1 plus x plus -6 equals 0?
Yeah, so equal to 0. And you said 1 plus x, so that goes because of the hydrogen, the x is because of the nitrogen, and then you said plus what?
-6.
Exactly, it would be -6. Why -6?
Because there's 3 oxygens, so you
And each of them has a -2. Exactly. So if you solve for this, what do you get? +5. So you see, it's not a charge. Nitrogen does not lose 5 electrons. It's never going to do that. So this is the oxidation state of nitrogen in nitric acid. So now you know everybody's. Hydrogen is +1, oxygen is -2, nitrogen is +5. Do you understand the process of what we're doing, everybody, besides the 4 people that always say yes?
I have a question.
Yes. What's your question?
All right, so like we we can look on the chart to find that oxygen is the same, hydrogen is +1. But how come we can't look on the chart to find nitrogen? We have to solve for it.
Because right here, Christian, right here, you see nitrogen? You see nitrogen has all those numbers?
Yeah. So so we solve and whatever number we get in those is the right one.
Right, it's gonna be one of those.
Okay, okay.
Okay, yeah, so that's why you have to solve for it, because you have an option of all of those, so you don't know which one it is. And that's the same thing for chlorine. It's the same thing for manganese, same thing for chromium, same thing for vanadium. So the ones that have more than one option, you got to solve for it. Okay, so that's why. The next polyatomic ion, does anybody know what that's called?
Permanganate.
Permanganate, good job. Who do I equal this permanganate equation to?
-1.
Good job. Okay, so who am I solving for here?
Magnesium.
Not magnesium. Magnesium is Mg, my children. That's manganese. Yeah, manganese. Okay, so what do I put? Tell me what to put for the equation.
We're gonna have a x plus -8.
-8, that's exactly right. Why? Because oxygen is -2, but you have 4 of them, so -8. Then you solve for x, so x is +7. See that? X equals +7. That's it. Super easy. Everybody cool with that?
Yes.
Okay, so can we do the last one quickly, please? Who do I equal it to? Actually, what is this called? Anybody know what it's called?
Dichromate.
Dichromate, good job. What do I equal it to? -2, right? Okay, so I'm solving for obviously chromium. So I would do -14, right? Because the oxygen is -2. And then what would I put for the chromium?
We put x for chromium. Oh,
Not
2x, 2x, 2x.
Yeah, good job. 2x. So solving for x, okay. Solving for x, it gives me +12. Yeah, so +6. So that's it. So the oxidation state of chromium is +6. The one of oxygen is -2. That's it. Any questions? Because now we're actually going to start talking about redox reactions. No? Oh, go ahead. Go ahead. Did you have a question, Camille?
No, I said no question.
Oh, okay. Okay, cool. So redox, here we go. The purpose of a redox reaction, which I think Camille had said at the beginning, or somebody said, Cherish, I don't remember, but is someone's transferring electrons. How do you know that someone's transferring electrons? You do this little thing that we've been doing. You assign everybody numbers, and then you see from one side of a reaction to another side of a reaction if the numbers have changed. If the numbers have changed, then you have transferred electrons, and therefore it's a redox reaction. I do want to point out that not every reaction is a redox reaction. For example, precipitation reactions. Remember we did those yesterday? If you assign, try to assign oxidation states to everybody in a precipitation reaction, nobody's numbers are going to change. So the numbers on the left, those little states, and to the numbers on the right of the reaction don't change. So therefore, that is not a redox reaction. Hold on a second, please. Hold on one second. Because it's really loud in here because of the thing. Hold on. Okay, sorry. So what was I saying? Oh yeah, so not every reaction is a redox reaction. Another example of that's not a redox reaction is a neutralization reaction. We haven't done those yet, but that's like an acid-base titration. When you put an acid and a base together, they neutralize. That is also not a redox, because if you put little numbers to everybody in the reaction, they'll all be the same. So that's how you can tell. If you use those little rules, that's how you can tell. Okay, so the point is to figure out who gets oxidized and who gets reduced. There's these little things that people use to remember, and one of them is oil rig, but the other one is Leo Gur. So I like this one because it talks about a lion. So Leo the lion, if you remember, Leo the lion goes grrr, right? He growls. So if you remember that, that'll help you understand, okay, if I lose electrons, I am oxidized. I'm undergoing oxidation, right? So a loss of electrons means oxidation. A gain of electrons means you are being reduced. Okay, is everyone cool with that?
Yes.
Okay, so that's how I would suggest that you remember it, or whatever, if you don't have to, but that's how I remember it. Okay, so let's try one. Yay, we're here. Okay, so we have to, the first thing would be to write down the reaction, but I've given it to you. And then the next thing would be to balance it, but it's balanced. But then the next thing would be, let's assign the little numbers to everybody. We've got to assign oxidation state. So what would be the oxidation state of the magnesium?
0.
0. Why?
Because it's a free element.
Perfect. And what about the oxygen?
0.
It's also 0. Why? Why is this one 0?
Because it's in its natural state.
Perfect. Perfect. That's excellent. That's perfect. Okay. So what is the oxidation state of magnesium on the right? Okay. How about this? What's the oxidation state of oxygen on the right?
-2.
-2.
Okay. So if this is -2, then what does the magnesium have to be?
+2.
Right, because remember, this is like, we're in our head, we're doing the little math equation, right? Okay, so you see how the numbers change? This is a redox. So I would do these little lines. I would go, okay, magnesium goes to magnesium and oxygen goes to oxygen. So let's do magnesium first. 0 to +2. Is magnesium losing electrons or gaining electrons?
Losing.
It's losing, right? Because it's getting more positive. So therefore, if I'm losing electrons, I am being what?
Oxidized.
Right, which is Leo. That's Leo. Loss of electrons means you're oxidized. If one is being oxidized, then the other guy has to do the opposite, right? So oxygen is gaining. It's going from 0 to -2. It's getting more negative. So therefore, this is the GER. Gain of electrons means oxygen is being reduced. Okay? Is everyone cool with that so far?
Yes.
Yes.
Okay.
Yeah.
Another thing you need to know for oxidation reactions is you need to know who is what agent. Okay, so let me say that again. Who is what agent? So for example, if you're being oxidized, right? If that person, if magnesium is actually being oxidized, if he's losing the electrons, he's giving those electrons to somebody else. So therefore, he's the dude that does the reducing. Does that make sense? He's being oxidized, so he's the dude that's doing the reducing for the other guy. Does that make sense?
Yes.
Does that make sense to everybody else?
I have a question.
Okay.
So does that mean that whoever, well, never mind. I got it.
Okay. So that means that this guy would then be the reducing agent, because you have to tell me what agent everybody is as well. Right? So, and it's always the opposite. So what I would do, well, let's obviously the other one, let's do oxygen, and then I'll tell you what I would do. GER, right? This guy's getting reduced. So therefore, he's the oxidizing agent. So then you would just put oxid agent like that. So there's all those things you got to do when you get a redox problem, right? You've got to make the reaction, balance it, put the little states, the little numbers, figure out who's Leo, figure out who's Ger, and then figure out who the reducing agents are. The agents are, reducing or oxidizing. So what I would do is I would do it in order, right? Because once you know who's Leo, then he's going to be always going to be the opposite agent. Once you know who's Ger, then that's automatically going to be the dude that's oxidizing the other guy. So he's the oxidizing agent. Are you guys okay with that? Any questions with that? No. Okay. So
I have a question. So with the reducing and oxidized agent, like how does that describe the product ish?
So it was sorry, it was hard to, your microphone's a little, can you say that one more time?
So with that, how does that so like in the reaction, so like how does that describe the product?
It doesn't describe it.
Oh, it does.
No, yeah, all you're doing is you're trying to figure out as the chemist, as the person behind the reaction, who is being oxidized and who's being. So I mean, it's telling you. Yeah, thank you. when the reaction goes on as normal, right? Magnesium, when you add magnesium to oxygen gas, it's going to react. But as for us, for information, right, we want to know, okay, well, who actually took the electrons, who gave the electrons, and how many were taken, how many were transferred. So it's just information, right? So it's information for us. I don't know if that answered your question. Did that answer your question?
It did.
Okay.
I kind of fixed it weirdly, but yeah, it did.
Okay. So this is just, all of this information on the side is basically for us so that we can know more about how the reaction takes place, right? So the only thing that makes a reaction go is if they're going to become more stable, right, at the end. So, but the process of that is what we're trying to figure out now. Like, okay, so who does it? Who gives electrons? Who takes it? If this is an electron transfer process, what's going on here? And we're just trying to figure out what's going on. So we're almost done. This is basically the bulk of what a redox type problem would ask you. The only other thing that you have to do is you have to denote or write, you have to be able to write the half reactions. And this is the part where I think people in the first section were like, what? You have to write the half reaction. So the oxidation half reaction and the reduction half reaction. So if you think about it, when you add up these two half reactions that we're about to write, we're going to do right now, if you add them up, you're going to get the actual reaction. Okay, so that should tell you that the answer to writing down these half reactions is already here. It's on the paper, it's on the board, right? So you're getting the information from the thing that you just made. So it's not like we're creating anything new, because if you do it correctly and you take the information down and you write it down correctly in these half reactions, you'll be able to add those two reactions up and actually get back to the original reaction, which is like we're going in a circle, basically, right? But again, it's for information purposes to actually analyze what exactly is going on and how many total electrons are being transferred in this particular reaction. Are we okay with that? Because we're going to start it now. Do you understand like the purpose of the half reactions?
Yes.
Okay.
Yes.
Okay, so the oxidation half reaction obviously deals with the dude that's being oxidized. Who's being oxidized here?
Magnesium.
Right. So the way that you write half reactions is literally you take the information from the reaction that's already there. So, but you have to take the element in the exact form. So let me say that one more time, in the exact form that it is in the reaction. So what do I mean by that? Magnesium on the left has an oxidation state of 0 because it's magnesium solid. right? So you would, and everything has to be balanced. So if there's 2 magnesiums, you've got to put 2 magnesiums in the half reaction. So all we're dealing with in this half is just magnesium. We're forgetting about the oxygen right now. It's just magnesium. So I would put 2 magnesium, okay, 2 magnesiums, and this is the oxidation side, right? The oxidation half reaction. So that means that magnesium has lost electrons. So the purpose of these little half reactions, again, is to show how many total electrons have been transferred. So you start out with magnesium, and then you go ahead at the end of the reaction. What has happened? Magnesium has lost how many electrons? Can somebody tell me? And think carefully. Don't just say what's on the board. Think carefully how many electrons magnesium has lost. Total electrons that magnesium has lost.
Would it be 4?
Exactly. It would be 4. Each magnesium loses 2, but you have 2 magnesiums. So therefore, the total amount of electrons that are being transferred in this reaction is 4. So you would put 4 electrons. The oxidation half always has the electrons on the other side because it's losing them, right? So you would have 4 electrons, and then you've got to denote what magnesium now on this side looks like. So can anybody tell me how I would write that? Hopefully you'll get it right. Somebody try.
I'll try, but can you repeat what we're trying to find? You said on this side we're trying to find magnesium?
Right, so this oxidation half reaction that we're doing right now is just going to show us what's happening to magnesium. So magnesium starts as magnesium solid, right here, we wrote it down, right? So how does magnesium look on the other side of the reaction? It's not a solid, right?
Yes, I guess.
I mean, it's a solid compound, but what is magnesium by itself in this solid compound? This is an ionic compound, right? So it's not, you're not going to write magnesium exactly like we wrote it here. How would we write it?
Two magnesium plus 2.
Yes, good job. Good. Was that Isaiah? That's what it would be. 2 magnesium plus 2, because it's an ion in an ionic compound. So if you notice, look what's happened. Magnesium started as a solid by itself, uncombined, and then it reacted and it became an ionic compound. So the form of magnesium is now an ion in this ionic compound. So that's what I meant by, like, you've got to tell me exactly what the correct form of the element is on either side of these half reactions. So that's it. That is how you would do a half reaction. So let's try to do that now for the reduction. Who's getting reduced? It's the other guy, right? So it's oxygen. What is the form of oxygen? What would I put on for oxygen in the reduction half reaction? Tell me what to write.
O2.
Okay.
And then I don't know if that makes sense, but like, is oxygen gaining 4 electrons?
That's exactly what GER means, gaining electrons. So how many total electrons does oxygen gain?
I don't know how to.
Wait, you cut off. You don't know how to what?
I don't know how to write that. I said 4.
Yeah, so you would just write plus 4E, like I wrote here for the magnesium losing. So plus 4 electrons. That means that oxygen, you add 4 electrons to oxygen, right? So that goes on the left hand of the reaction, and then what goes on the right?
O.
2O.
Minus.
Sorry.
Well, not just O, but 2O2. Sorry, my bad. Not, did you guys say 2O2? That's wrong. It would just be 2O, 2 minus.
That makes sense.
Okay. Does everybody understand what we just did? Because that's it. This is it. I'm not lying now. This is it for a redox problem. That's all you need to know. You need to know how to do all of those things right there on the screen. And if you notice, look, you have 4 electrons on the left-hand side and you have 4 electrons on the right-hand side. That means that you can cancel those out. So that's what I meant. Like if you actually, at the end of this, if you were to take those 2 half reactions and add them, quote unquote, add them together, you get back the original reaction. And I have it nice and neat because this is a slide from a long time ago. I have it nice and neatly written in the slide. So that's what we did. This is the oxidation half reaction for the magnesium. Oh, there. And then this is the reduction half reaction for the oxygen. And then you would add all of those, add those 2 half reactions together, right? And then obviously the electrons would cancel and you're left with the original reaction. That's the point of doing these half reactions, is to make, it's kind of like to tell us how many electrons are being transferred and making sure that we're doing it correctly. And you notice everything is still the same. Everything balances. That's why we brought the 2 down and all that. Everything makes sense. So it's kind of like a check. Are you guys okay or not okay?
Surprisingly, I'm okay.
Yeah, good. Excellent. So that's it.
I have a question.
Yeah.
Would we balance, wait, with the original
Yes.
equation?
Your question, Kezia, is yes. Always balance. Always.
No. So
Okay.
would our oxidation, the half reactions, would they be after we balance or before? Before, right? I mean after, right?
Yeah. How do you know? Yes, yes. Everything starts from the main reaction, right? So you do the, like I said, the protocol is get the reaction, balance it, put the states, the little numbers, and then find Leo, find Ger, find the 2 agents. So do all that information first. The last thing you do is then figure out what the half reactions are, because the half reactions have to make sense with the main one, not the other way around. So yeah. Any other questions? Now I want to do another one. We actually didn't do this.
Will the oxidation chart be on be a given for the exam?
With the HUNA?
Like the
chart? The periodic table?
no.
You mean
If you
this?
showed us.
This?
Yes, that.
Nope.
Okay.
Nope. So that's why you have the rules. You got to know the rules. If you know the rules, then you don't need the chart. This is just to show you as a whole, look how many different types of oxidation states you have. But you don't need it. If you know the rules, then you know how to do it. So that's why you have to apply the rules. Yeah. So let's do this one. Tell me what the oxidation state of cesium is.
Zero.
Okay. Oxidation state of bromine.
0.
Okay. Oxidation state of cesium bromide, or in that compound, cesium and bromine. What is it? Come on, guys.
1.
You were cut off, Camille. Say it again.
Cesium is +1.
Okay, so what's bromine?
-1.
Okay. So what is the next step?
Determine which one oxidized and which one is the reduct. Yeah.
So this goes to this guy and this guy goes to this guy. So cesium is going from 0 to +1. Is it being oxidized or is it being reduced?
Oxidized.
It's sorry?
Being oxidized.
That's right. So it's Leo. It's Leo, right? So that means that this dude is Gur. So simple. So if that's Leo, what agent is he?
Reducing agent.
Okay, this should not be hard. Everyone should be jumping at answering this. It's always the opposite. So this guy is the reducing agent. So that means that this guy is the oxidizing agent. Yes? Everybody? Hello?
Yes.
Yes.
Okay. See how fast we did that? That's it. That's literally what you need to do for a redox problem. So is this a redox? Yes, because there's a transfer of electrons. You see the numbers changing, so therefore it's a redox. So now let's do the half reactions. Oxidation, half reaction. So what would I write?
2CS,
Okay.
and you go to you lose 2 electrons.
So you mean yield?
Oh yes, yield.
Uh-huh. Okay. Yield.
And you lose 2 electrons,
Okay.
and plus 2CS plus 1.
You see, this is easy. Good job. All right, so somebody else, reduction, half reaction. Let's go. Come on.
It's gonna start with VR2,
Okay.
and it's going to gain 2 electrons, so it's plus 2E.
Okay.
It yields to 2Br minus.
2Br minus 1. That's it. This is not hard. It's really easy. If you get it, if you get the process, it's simple. So that's it. That's it. You've done everything. Good job. I think we might have time. Yeah, we got time to do another one. Look, let's check our work. Did we do it right? 2CS, CS plus, and 2 electrons. Yup. 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 Okay, look at that. Boosh. Easy. Let's try some other ones. So, how about, which one do you want to try? We don't have time to do all of them. So which one do you want to try?
The 3 magnesium.
Okay, that's the one I was looking at actually. So let's do that one. So what are the oxidation states of everybody here? And I should have given you states, but this is a gas, this is a solid, whatever. And that's an ionic compound. So what's the state of magnesium? Oh, wait. What's the first thing we should do?
Balance.
Oh, we should write the oxidation.
Yeah, we should balance it, but is it balanced? We always got to remember, we got to ask ourselves that. Don't forget, right? So for example, look at this one, right? The last one, that's not balanced. And I think this one here also wasn't balanced. You picked the one that was balanced. Of course you did. But anyway, so, okay. What's the state of magnesium?
0.
Okay. What's the state of nitrogen?
0.
Okay. What's it? Oh, Lord. What's the state of magnesium on the other side?
Plus 2.
Okay. What's the state of nitrogen on the other side?
Don't we have to solve for it?
I don't know, you tell me.
I think we have to solve for it.
Okay, let's do that. So what would I equal it to?
0.
Okay. And then what would I put?
You would put 2 plus, no, not 2, 6 plus 2x.
6 plus 2x. Good job. So x is equal to what?
3 or -3.
-3. You see how that's different than the other one that we did? The other one was +5, right? So yes, you have to solve for nitrogen. So this is -3. So there you go. You have figured out the oxidation state. Next, what do we do?
Figure out which one is being oxidized and which one is the redox.
Okay, so Leo Gur, right? So who's Leo and who's Gur?
Magnesium,
Magnesium.
is the Leo.
That's right. Magnesium is
Gur is nitrogen.
It's like once you figure one out, then you know everything else for the other guy, right? So yes, so the nitrogen is the GER and magnesium is the Leo. So Leo is what agent? I'm sorry, Leo. Well, what did I just ask? Magnesium is what agent?
The reduct
The
agent.
redox agent.
Yes, not the redox. No, okay, make sure you say it correctly. Yeah, the reducing agent, not the redox agent. I don't know what that is. Right? So the reducing agent. Okay, good job. And then obviously this guy is the oxidizing agent. Yeah? Everybody cool with that? Okay, so let's do some half reactions. We've got time. We got a minute. Let's go. So oxidation half reaction. Tell me what to write.
I'm gonna write 3 mg,
Okay.
and then we're losing. We're gonna be losing. What is that?
So if I'm losing, what side is it on?
It's gonna be on the yield side, right?
Okay, so you didn't say yield, so I'm confused. See how I'm confused? I'm confused.
Yeah, my
Right,
bad. So
you say
yielding.
yield. Okay, good. Now I understand. So how many?
We're gonna be losing. Would that be 6 electrons?
How about you ask your friends? I don't know. You tell me.
Hey friends, would that be minus 6 electrons? Because there's three of the magnesium, and they're each oxidation level is 2.
Somebody
Yes.
help him. Okay, good. Good job, Christian. It is 6 electrons. Excellent. Plus what? What is the form of magnesium on the right-hand side?
On the right hand side, it's gonna turn into a gas, right? Or
What?
now it's gonna be a solid.
What? No. Stop. You're giving me an ulcer. What form is, I'm not asking for gas, solid, liquid. I'm not asking for that. I'm asking like, what do we write? Like, remember we wrote here, like the form, BR, that's what I'm asking. Like what form? What does it look like? What does magnesium look like on the right-hand side?
Oh, it's gonna look like Mg3.
Wrong. That's wrong. That's wrong, because if you say Mg3, that means that you've got 3 Mgs connected to each other, right? That's what the subscript means, right?
Mm,
So it's
so
not
then
3 Mgs connected to each other. It's not a compound of 3 Mgs. So what type of compound is this? It's really easy, dude. What type of compound is this? And when you have a magnesium and a nitrogen together, what type of compound is it?
so that's gonna be ionic.
Right. So it has to be in the form of an ion. Look here. This was an ionic compound. Cesium bromide was an ionic compound. Look how we broke them up. See, they're in forms, they have ions, they're charges. So it's got to be in the form of an ion because it's an ionic compound.
So would it be 3m plus? I mean, no, 3m minus. I mean, 3mg minus, or
Magnesium is a metal. So magnesium can never, and it can never have a negative charge.
so it'd be 3mg plus.
Okay, stop. Why did we do a +2 up here when we did this? Why did we put a +2?
Because that's the oxidation state.
But why, but also what is that? If I asked you what is the charge of magnesium when it becomes an ion, what would be the charge of magnesium?
It would be positive.
Positive what?
Positive 2.
Why?
Right? Because that's how many electrons would be gaining. I mean,
What column is it in?
it's in the second column.
It's in column 2.
Right,
Column
it's in
2.
column 2. So therefore, it loses 2 electrons. So when I ask you what form, how does magnesium look like when it's in an ionic compound, it can never be a negative because first of all, it's a metal. You can't do that. So it's basically asking you, how does magnesium ion look? So what charge does magnesium ion always take?
Positive.
Positive. Christian, you got to say the whole thing, dude.
Positive 2.
2, yes,
Positive 2.
+2. So you have 3 magnesiums. So therefore you would write 3 Mg2+, because that's the ion, that's how it looks. And you would just happen to have 3 of them. You get that or no?
Yeah, my bad. I thought it would be okay to just write 3Mg plus, but you gotta write the.
Yeah, and absolutely not.
Yeah.
Mg does not take a plus charge. It's 434, so I know I'm really late, so I'm just gonna write what the reduction is. The reduction half would be then N2, wait, 0 to +2. Oh, I did this wrong. Yeah, so this guy's gaining the react. Yeah, sorry, my bad. So this would be 6 electrons goes to this. And then the form that this looks like would be 2 and 3 minus. Okay? Is everyone okay with that? I know we are not going to really talk about it, but that is what the answer is. And I stopped sharing, didn't I? Yes, I did. So sorry to keep you so long. It's 5 minutes after. Anybody have any questions? Any quick questions that you want to ask?
So for redox reactions, will we be given the product that it yields, or we have to figure it out?
I don't know yet. I've done both, so it depends on how I feel when I make the exam. But expect that you might have to know the products. But if you, it won't make it hard. I'll make it. For example, there are some redox reactions that you should know what the products are, like a combustion. Okay. Or if I tell you it's a combination, then you basically, that's telling you the answer. You combine these 2 elements into one. So we haven't talked about the different types of redox reactions, but I have been known to ask, to not give you the whole thing. I just say, okay, so if you have a combination reaction and you have this and this as the starting material, can you tell me who's the Leo, who's the Ger, who's the blah, blah, blah? And I wouldn't tell you a product, but I told you it's a combination reaction. Does that make sense?
Okay. Yes.
So any other questions? Okay, guys, you guys did a lot better than the first section, I think, for the people that were communicating with me. So on Monday, we're going to talk about redox again. And then we talk about dilutions and titrations, and that's it. It's test time. So please do not wait until next week. You've got to practice this, obviously. Okay? If you guys have no questions, then I will let you go.
Thank you. Have a good day.
Thank you. See ya. Bye.